group to the complex numbers. It turns out it's a special kind of function. So a function, let's call it f, from the group G to the complex numbers is called a class function. If it has the following property. If I evaluate it on something in the form GHG inverse, it's equal to f evaluated at h. And that's for all pairs of elements G and H in the group. In other words, it's a class function if the value in an element only depends on the conjugacy class of the element. If any two elements in the same conjugacy class give you the same value for that function. That's a class function. Anyway, the claim is characters of representations are in fact class functions. Why is this? Well, what's the character applied to an element like GHG inverse? Well, by definition, that's the trace of the representation at GHG inverse. Of course, that element is a product, phi G, composed with phi H, composed with phi G, and I can say it's the inverse of the operator. But hey, that's the property of a trace. If you conjugate an operator by something, the trace doesn't change, so that's actually the trace of phi H. In other words, that's the character at H. That's the proof. It's just from the conjugation invariance of the trace. So characters are not just functions from the group to C, they're class functions. So let's establish some notation. I'm going to write, following Steinberg's book, L of G, that's the set of all functions from the group to the complex numbers. And now I'm going to write L to the CG for the subset consisting of class functions. The book uses a different notation for this, but I don't like it. So I'm going to write this. C stands for class function. Let's notice these are both complex vector spaces in the obvious way, because I can add functions and multiply them by scalars. The class functions are a subspace of the space of all functions. We can even say what their dimensions are. The dimension of the vector space L of G, well, G is a finite set, so it's a finite dimensional vector space, and its dimension is just the order of the group, because a function is just determined by its values on the elements. The subspace, well, it's determined by its value on one representative from every conjugacy class. So this dimension is the number of conjugacy classes in G. That's the dimension of the space of class functions. Now, it turns out there's a little bit more structure here. The space of functions on the group has the natural structure of an inner product space, and more precisely, a Hermitian inner product space. Let me say what this is. So we can define the following. If I have two functions on the group, I'll write angle brackets f1, f2. That's defined to be the following. I'm going to take the sum over elements of the group of the value at f1 at G times the complex conjugate of the value of f2 at G. And then I'm going to take the whole thing and divide it by the order of the group. So this is really a function from the product set LG times LG, pairs of functions, and it gives you a complex number. So I'll write this as that. I call this a pairing. So this has some properties that are immediate from the definition. First of all, it's linear in the first variable. So let's say I have lambda 1 f1 plus lambda 2 f2, comma, I don't know, f. So here, f1, f2, and f are functions on the group. Lambda 1, lambda 2 are complex numbers. Well, if that's put in there, I can pull it out. So I get lambda 1 times the pairing of f1 with f plus lambda 2 times the pairing of f2 with f. Second of all, if I pair f2 with f1, that is, I change the order, it's not quite symmetric. Instead, I have to put in a complex conjugation. That just comes from that formula. 3, if I take the pairing of a function with itself, that's always going to be a real number. In fact, a positive real number if I have a function which is not the zero function. That's just because if f1 is f2, then each term here is f of g times f of g conjugate. And you know that's the length squared of the complex number f of g. And therefore, if the complex number is non-zero, the length squared is positive. In other words, this operation is an example of a Hermitian inner product. So it's the properties of a dot product, but modified for complex numbers to take into account this complex conjugation. It's a Hermitian inner product on the complex vector space L of G. Notice from properties 1 and 2, property 1 says that the pairing is linear in the first variable, but from property 2, you learn that the pairing is antilinear in the second variable. So you'll get complex conjugates of these scalars. By the way, since the class functions are a subspace of the space of all functions, that also gets a Hermitian inner product just by restriction. Because of this, we can talk about things like the following. We can talk about an orthonormal subset of L of G, or of the subspace of class functions. That's a list of functions, let's say f1 through fs, such that if I pair fi with fj, I get either 0 or 1. So writing that with the Kronecker delta, you get 1 if I equals j, and 0 if I is not equal to j. That's an orthonormal subset. You can also speak of an orthonormal basis. So that's an orthonormal subset, f1 through fs, which is also a basis. And we could apply this to L of G, or just perhaps of the subspace of class functions. Notice, if I have an orthonormal basis, then, let's call it f1 through fs, then for any f in the space, we have the formula f is the sum of f paired with fk times fk, as k runs from 1 to s. This gives an explicit formula for writing f in terms of the orthonormal basis.